All right, good afternoon, everyone. Any questions? Yes?
I just wanted to get I saw that we don't have any homework next week, and then on the week of the exam. Do we have homework that week as well?
Yes, you do. So the idea was that people wanted no homework the week before the exam so that they could spend all of that time in studying. And, whatever, it seemed reasonable. So originally it was that there was no homework during the exam, but now that we've moved the exam by a week, there'll be no homework before. It's awkward the week after, I think, during Thanksgiving. What I'm going to do is I'm just going to put all the homework tomorrow, the day after, on the so that you have it and you can choose to do whenever you want to do it. Other questions? All right, let's get going and see what questions arise. We are here. Yeah, so one of the things that's important to do these kind of linked list things, as you have found out, is to be able to draw these diagrams, right? So if you can't draw the diagram, it's unlikely that you can code it up. I certainly could never have done the previous homework assignment without sketching up what is supposed to be happening first. You have all of these links that move in crazy directions, and so it's an essential skill to be able to draw these diagrams. And so I used to just have students draw kind of random diagrams, and the difficulty with that is that then you get a lot of diagrams that are pretty ambiguous. So students would draw things like this, and then you don't really know what goes on in the student's mind at this point. Maybe it's the right thing, maybe it's not. And so what I'd like us all to do is to follow the style of the book and drawing those diagrams. And so I want to practice that a little bit before going on to the next section. And so the style of the book is very prescriptive. It says that you have these blobs that are the objects, and each blob has a type, so that might be node, and it follows what's called the UML standard, and so the type is underlined. I don't care about that part, but I'll do it anyway for consistency. And then a node might have fields such as data, and so the field has a name and some contents, and next, same thing, name and then the contents. And you might, of course, have multiple of these, so this is a little easier for me to do. Because I can copy and paste here. You won't be able to do that in the exam, unless you have a program like this. So now let's see what we can put into this data and next fields. So data could be like a string, like call. And the next thing would be an arrow to the next one, or maybe null, if it's null. So now this is completely unambiguous, right? Now you know exactly what is going on in this diagram. Now if it's a linked list, you might even want to say, okay, they're not just nodes, but there's also the object that gets us there. So that has type linked list. And it has a reference first. Maybe it has a reference last, but right now we'll just use one that just has that points here. And maybe you have an iterator. And it had what, a previous, was it called current? I don't remember. Yes, current? Hmm? Yes, okay. And so then this one here would go here. And so in the book, the artist who drew these was very careful to make the layout so that the arrows look nice. You know, here we don't really care, so if this thing, you know, goes all over, then that's fine. What's important is that we see where these things point. So now let's say that there's some piece of code that advances the iterator to the next position. Right, so that code would look like, where do I don't have space to put it anyway. Let's say the code looked like this. Current equals current next and previous equals current. So what the book then does, and that's what we also want to do here, is it gives these nifty numbers here. And so now we'll draw it with the numbers. So we will have current equals current.next. So then, you know, you can't really cross things out in these diagrams. In the book, we can operate with like multiple things, but if you do this in an exam or just on a sheet of paper, you know, it's not that easy. So you just have to put it in. Let me not use the null here actually, because I want to, you know, show a somewhat more common scenario. So this would, you know, then go on here to the next node over here, which I don't really have room for. So in this case, I would say current equals current.next. Okay, so here is current. I follow along. Current.next is the blob here on the right. So now then I would have to do that. And so I'll use dashed lines so that it looks a little different. And then I write the number 1 here to indicate that that's the step that I've just done. And now it says previous equals current. Okay, so what is it set previous to? So it says previous equals current. Now current points here, so I guess that instruction says previous should also go here. That's step 2. So that faithfully reflects the 2 steps that I had there. But what's the problem? Yeah, so the fact that there's stony silence right now points to a limitation of this technique. So the drawing the arrows technique can really only work if you have some basic ideas of what the arrows should look like. So you have to have some idea of how previous and current should be located to see whether they're in fact correctly located. So what should be the relationship between previous and current in an iterator? Excellent. Previous.next should be current, right? So previous should always be 1 before current. Is that the case right now? It isn't, right? Because as it happens, previous points to our blob to the right, and current also points to the blob to the right. So that means that one of these instructions that I wrote were wrong. We only had two, step 1 and step 2. Which step was wrong? Yeah, so this one here, as it is, doesn't really work. Can you fix it? Aha, that would work. I could put it first, or that's too difficult for me right now to rewrite everything. What else can I do? But putting it first is actually probably the better way of doing it. But give me a second possible fix. That would only work if I had a doubly linked list. So, which right now it doesn't look like it. Previous.next, that'll work. So now I'm going to have to see how I can erase here. Not that easy. And now, let's see, previous equals previous.next. That means that now previous actually points here. So that's the basic idea behind these diagrams. See, so on the slide it says, be familiar with the layout for an object. An object has a type that would be like here, the node, and it has some contents. It has a bunch of fields, and each field has a name and a value. And the value could either be a string or a number or some such thing, or it could be a link to something else. So that's the basic syntax. And then you use the circled numbers for the steps. And so when in an exam there's going to be a question that says, draw the memory layout before and after these steps, then the expectation is that you use this exact same notation and not something that, it's just some basic random boxes and arrows, but use this exact same notation. So here's from the books where you can see this. And so I don't expect, of course, the level of beauty that they did in the book. And in the book they had the great advantage that they can do the before and after, and we can try that. It's just more drawing. So if it's certainly a reasonable alternative to do it with the before and after. So I'm going to try this. So have a look at my solution to homework 10A. I was actually surprised that I got no complaints that I forgot to post homework 9 solutions. Does anyone look at these solutions? So you're supposed to look at those solutions to see if they're any better than yours. So go and look at the homework 10 solution. Do it right now. They are, just in case you've forgotten, in Canvas. So in the files area, the other reason why you might want to look is if accidentally I put in one for the next one. So here it comes. So here we have homework 10A, solution. And so it's the reverse first n here. And so we're having here this test case here. So here's what I want you to do is get out a sheet of paper and Now we're going to be calling names.reversed first n of 2. So what do you have to draw? Where's my test case? So go ahead and draw this linked list. Now, this linked list has 5 nodes. You probably don't have to draw all 5 of them, although you certainly could. Draw at least 3 because we're reversing the first 2 links. And then do a dot, dot, dot. And so you don't have to trace like every one of these calls. I'm trusting that you know how a linked list looks. So let's say that you know what it looks like here. Notice, by the way, this thing these are always calls to add first. I don't quite know why. Did we not have an add last in this implementation? Yeah, that's why. So this was a very simple implementation of a linked list, and it didn't have an add last. So it only calls a add first. But so I'm very much hoping that you now realize that the list then is going to be built up in reverse. So the first 3 elements are Bill, Dick, and Harry. So draw 3 nodes, and maybe more if you like, for the remaining elements. Each of these nodes, as you know, has an element data and next, just like what I just showed you. The list itself has a node first, and so make sure that you get those drawn nicely. After you're done with that, then it's time to trace into this reverse first n of 2. And now here we have a bunch of variables: previous, current, and next. And so those are the ones where we want to see how do they update themselves. And what else updates? Oh, this one here, current.next updates itself, right? Something exciting happens here with first. And so go ahead and do that. I would say that's going to take you, at least 5 minutes to draw that. And then I'll have a look and see what you've done. All right, so let's go through this here. So here's what I would do is, we're not in this situation. So note previous is first, so that's the first thing I'm going to do. So I'm going to number this as 1. And so now let's see. So previous is first. So, and I put like a 1 somewhere. Now it says current is first dot next. So current is first dot next. That's this one here. So we'll label that with a 2. Okay, now it says first dot next equals null. Okay. Don't know why, but so it does. So now, of course, we have this thing in here, and I could cross it out, and so I'll start crossing it out, and I'll label this thing here as 3. And now I have int count equals 1. So someone said, what should I do with count? With like extraneous variables, if I feel that I need to keep track of them, then I would just put like a traditional little table here, because it's the pointers that matter, and I don't want to clutter up the thing indefinitely. So here I'll just put the count like this. Maybe I won't even need it. So current is not equal null. No, it's somewhere. So node next is current dot next. So that's this one here. So that's a step. Let's label it as 4. Next is current dot next. So that would go. Oops, I went blue. Okay, now it says, no, I'm sorry, I was all wrong. This one is 4. This one is 5. Current dot next is previous. Okay, current dot next equals previous. Okay, previous points here. Current. Oh, why does it say current dot next to null? Oh, we had first or next to null. Okay. Current dot. Oh, because so I was wrong. I set the wrong thing to null. Yes, I did. That's unhappy. So this one was still correct, but then here I have to set this one to null, right? In step 3. So what's the lesson from this for the exam? Bring an eraser. All right? I can do so. Yeah, don't do this in pen, unless you are smarter than I am. Then, yeah, it's totally easy to make these mistakes. So all right. So now next is current dot next. Next is current dot next. So that would be this one here. Current dot next is previous. Current dot next is previous. Okay, whatever. Current dot next. Oh, that's this one here. Okay, so now that one now points back here. So at this point here, it could be helpful to use different line styles. So it could start, with maybe with a dash line style, to make the evolution a little clearer. That's something worth experiment. Previous equals current, so that's step 6. Previous equals current, so now previous points here. Current equals next. Current equals next, so now we're here. That is step 7. Okay, now are we done? What's count? Count is 1. It's less than 2. So now count goes to 2. And so I guess I should write my count here. So it used to be 1, now it's 2. So now I have to do this one more time. And so the way that you just write more bubbles here. So now this is number 8. Next is current.next. So that's the one that's current is now here. So it's important that you kind of have an evolution in mind. That's why I suggest that you change the patterns of the lines. Now, of course, if you had infinite time, you could redraw the whole diagram a few times. But who has that kind of time? So changing the style of the lines, changing the color is also a good thing. So if you can swing it, get like a few color pens. Yeah, maybe you can loan them and return them later. And that way you could alternate the color a little bit so that in your own mind it's clear what is what. I mean, the numbers clearly help, right? Here we have a thing that's numbered 2. Here we have one that's numbered 7. And so it's clear that the 7 must be the later one. But still, every bit helps to distinguish that. So, okay, next is current.next. That was 7. No, now we're at 8. Next is current.next. So now we're back here. That's 8. Current next is previous. Okay, current next is previous. That now, so now there appears to start being a pattern. You can see how these links reverse. Previous equals current, and current equals next. Yeah? It just incremented. Yes, so that's happened here.
Yeah, but how does it?
Well, the check is only. Yeah, but the check is only up here.
Yeah, but count starts at 1, then you increment count first.
Oh. Oh, I see. You're right. Okay. So we're done.
Yeah.
Okay. Oh, good. Okay. All right. Okay, I'll buy that. So now, is it actually working? Did it reverse the first 2? Oh, we're not quite done. Now we're falling down here. Aha. So now so I was wrong with these ones here. Thank you. See, this is harder than it looks. Okay, now it says if current's not equal null, first.next is current. So this 7 was still okay. First.next, that's this one here that at one point was set to null, is now current. And current is here. So this is step 8. And first equals previous. Oh, previous has been moved to here. This is from 1 to 6. So first is previous. And so this here was step 8. And this was step 9. First equals, so here that's step 9. Okay. And so now let's see. So the linked list now goes along this trajectory. I don't know if you can see my pen here. See if I have a highlighter. Okay. So it goes along here, then it goes here, and then it goes, amazingly enough, it goes here, and the first 2 have been reversed. All right, so it seems to have worked, and that ran through this thing. And you can see how tedious it is. So the numbers help. Different patterns of line styles help. Different colors would help because, how are you going to have a third line style? Are you going to have like a difference between dashed and dots? I mean, if you're a very good artist, you can do that. You go to wiggly lines or something. But, colors are always good. So I'll give you some exercises to practice this, and so that before the exam, so that you get some hands-on practice. So let me have a quick look at. Okay, and so here we have someone when it looks exactly like what I wanted. You see some dotted lines and stuff. over here, the student redrew this here because it was getting complex. The trick is to try to keep it in one diagram. I will not give you something in the exam that's so crazy that you have 4 different values for each, and so you should be able to keep it in a single diagram. So try those things out. Of course, when you do this kind of stuff at home, to see whether your code is correct, it really helps to do it like I don't know if you have a whiteboard at home, maybe not, right? But I mean, if you have a whiteboard, it works great, because then you can just write these things out in real time. If you have like a drawing program like the one that I have, it also works pretty well, because then you can just redraw it, or you can erase if you have a pencil. So it is a super useful skill to be able to do these kinds of diagrams, and so I really want to make sure everyone can do that. And so it used to be in the past that it was kind of a spectator sport. The instructor would draw the diagrams, and the students would watch with more or less concentration. But the time has come for you guys to do it. So the other thing, for those of you who have not yet seen this, so I have this practice activity, courtesy of the textbook publisher, where we're trying to make sure that students can really understand how these diagrams work. And they're pretty nifty. So here's a linked list. You click on Start to Begin. And then, since this is just a bunch of JavaScript and it can't have you really draw things, when a new node gets drawn, it draws it for you. And then it says, now initialize this variable here, put in the data, I think it was Peter, and then this one goes here, and this one goes here, and presto, we have added a node to this linked list. So I'll put on more of those. I have them for doubly linked lists and for other things as well. And I could produce them for more things if there was popular demand. They're really useful for getting as a precursor to drawing your own diagrams. So if you haven't tried those out yet, by all means do that. Students who did class tests with these last semester said that it was oddly addictive to do this. All right, so let's get on with the actual lecture. So today we're going to be talking about array lists. So we're seemingly done with linked lists, but they will come back soon enough. So you learned a long time ago that in Java there's 2 data structures for collecting a linear sequence of numbers. You could use an array, or if anything for that matter. You could use an array, or you could use an array list. And you learn how to choose between an array and an array list. When do you use an array? There's only one reason to choose an array in practice, and that's because the instructor tells you. In all other situations, you would use an array list because the array list grows and shrinks on demand, and what's not to like? I mean, who wants to be constrained to a fixed size? So an array is a low-level type that's there in the virtual machine to build higher-level types such as the array list. So, the only other reason that you might use an array is if you have a very large collection of primitive type. If you have a huge collection of integers or a huge collection of doubles, then it would be inefficient to use an array list. But they're working on that. I was just at Java 1 and I talked to the guy who's working on that feature, and around Java 9 or Java 10, well, I think realistically Java 10, the Java virtual machine will automatically make it so that array lists of integers are perfectly flat and they no longer store objects. So we'll all look forward to those happy times. But in the meantime, we want to use array lists when we can. So what goes on in an array list? It's a simple concept that an array list contains an array. It manages the array for us, and it has a capacity. The array is a little longer than what's needed, and we also remember the current size. So right now, this thing has a capacity to hold 10 elements, and there's 3 in there. What if the time comes to put in the 11th one? Then it grows. Do I have a picture of that? Yes, later. All right. So most of the operations on an array list are simple. So here's the get operation. It checks whether the argument is within bounds, otherwise it gives an exception. And if it is within bounds, then it returns the position that we're at. That's, of course, O of 1, because the checking here, there's a few instructions to make this check. but not very many. There's a couple more instructions to fetch the element, but those don't depend on the position at all. They're constant time, 6 or 7 instructions. Now, to remove an element is a little bit harder. When you remove an element from the middle of an array, as you know, you want to remove this element, say, then you have to close the gap by moving these other guys up. And that is somewhat expensive. How expensive? So here you have the loop that you've seen in 46A on how to do this. And so that's the expensive part of removing. Now, when you say you remove the kth position, one doesn't exactly know where k is, but on average, if you make enough removals, some at the middle, some at the beginning, some at the end, the average location of the removal is somewhere around the middle. So that would be at n over 2, and then you need to move n over 2 elements, whatever is past it. And so the efficiency is O of n. So if the array has, say, 1,000,000 elements, on average, when you remove one, on average you have to move 500,000 of them. Sometimes you might have to move 999,999. Sometimes you have only to remove a few. But on average, it is 500,000. That's for a 1,000,000 array. If the array has 10 million, then on average you would have to move 5,000,000 elements. So it's an O of n operation. All right. So here we have a clicker question. Get a Piazza. All right, so let's see. So the first answer here is it's O of n, since remove last calls remove, we've just determined that remove is O of n. And so isn't it O of n to call an O of n operation? Seems plausible. This one says it's O of 1 since it does a constant amount of work independent of the array size. That's kind of plausible too, though, because when we remove at the end of the array, so the array could be huge for all I know, but to compute the size, you know, that gets me here, and now there's actually no element that I need to move because there's nothing behind it. It's O of n squared since both remove and size are O of n. What does size do? So did we have an implementation for size? No. But size, all it does is it returns current size. Well, that can't be O of n. It's not a linked list, right, where it has to find the end a link at a time. So size is clearly not O of n. So C has got to be wrong. Oh, I should stop this poll. And so I did actually manage to get one person to buy into D. And D makes no sense, right? There's nothing that gets cut in half here. And so, yeah, I had to come up with some distractor. So it's between 1 and 2. And so it really is 2 because in the situation of removing the last one, it doesn't depend on how big the array is. You go through the loop, you do no work in the loop that shovels other elements forward, so that's constant. You always do no work. And there's a little bit of extra operation, you know, to get there and to adjust some counters. But that's constant. It's independent. It's as fast to remove the last element in an array with in an array list with 5 elements as it is to remove the last element in an array list with 5 million elements. So it's independent of the length. The amount of work is constant, and so it's O of 1. So removing the last one here is O of 1. All right. Now adding is very much like removing. If you have a list and you want to add something in here, then you have to move all of these elements down. And so on average, that is, it's n over 2 elements that need to be moved. But there's one extra twist to adding that complicates the analysis. And that is, what if the array list is completely full? And as you know, that can happen, right? Over here we had a picture of an array list where the capacity was 10 and it only had 3 elements. Well, what if you add another 7 element and then you add one more? Then something has to happen. And what happens is, of course, we grow the buffer. Oh, I was hoping I had a picture. Okay, we'll just make you the picture. So we had an old buffer. We now make it twice as large. We copy all of these elements over. And then, so the previous buffer was this one here. And then we adjust this reference to the new array. What happens to the old array? What's it do? It slinks away in shame. No, right? What happens to it? Eventually it gets garbage collected. So no one remembers where that old array was, because there was before only a single reference to it, namely whatever was in buffer. Now buffer is relocated to point to the other one, and so no one remembers where that old array was. Eventually the garbage collector says there is a lonely unloved array, and it gets reclaimed so that it can be given out again later. So clearly growing the buffer is expensive. It's an O of n operation, right? Because you have to move all the n elements over to the new buffer. So that makes it seem like adding an element to the end of the list is potentially very expensive. You know, most of the time it's cheap. Most of the time it's a constant operation because you just add it to the end where there's still room. But every once in a while you have to pay a lot of money for it. And so the way I like to look at it is to well, so yeah, let's look at the cost first, right? So let's just assume for the sake of the argument that each time you add an element, you had a question.
For the buffer, why wouldn't you just make the array list bigger at the beginning? Like, I don't understand how it's not giving the error when you add a new element beyond the size of the.
I'm sorry. Why? Well, it would give you an error if you add it, but we're doing so much more. We're making a new buffer of twice the original size.
Instead of doing that, when you declare your array, why don't you just make it so long?
How long? Let's say that we're supposed to read in like all the words from a file. How long would it be?
Until the end of file.
But how do you know? You haven't seen the file. So we're prompting the user for the name. We're writing a program where the user is asked, which file would you like this program to read? And now you need to size the list for all the words in it. Ah,
Can we just do file.size? I understand file.size.
but you don't yet know what that file is because, oh, I see what you say. No, you could. In Java, you could, yes. So you could do that, but that still would be pretty wasteful, right? Because if that file was very large, the number of words could be 1/10 of the number of characters in the file. And so you could, in many situations, I agree with you, you could size it large enough, but you would waste a lot of space. And so yeah, so a billion, I guess you could do a billion, but if every array was a billion, right, at some point that would not be very useful either. So we really do want to have a data structure that grows like that. It's the same thing as we'll see next in the next couple lectures. When you have a hash table, you also want to be able to have it grow on demand. So this growing on demand is a useful thing. So you start out with something small, and every once in a while you say, okay, that wasn't quite good enough, so we're gonna grow it, or as you'll see in a minute, we're gonna shrink it. So that is a useful technique to be adaptive to the size of whatever the task at hand is. So, but I mean, I agree that in many situations you could have an upper bound of what you want to, but it's just kind of wasteful. So here's the money model that I think explains pretty well what goes on here. So we're starting with an array of size 10, say, and I'm going to say that each time that you add something to an array list, and you don't have to resize, it costs you $1. So you're putting in the first element, that's $1. The next one, now you paid $2. The next one, $3. After the 10th one, you've paid $10. Now the 11th one, that's going to be expensive because you have to pay the $10 for the relocation and another $1 to put in the element. That goes on for another 10 elements. And now, oops, you have a penalty of $20. And that goes on for next 20 calls. And then the next call afterward costs you $41. And then you have 40 calls, or 39 calls, I guess, that are cheap. And then the next one costs you $81, and so on. So that's the cost of inserting elements. And now that sounds like it's getting hideously expensive, but if you look at the pattern, so now you have 1, 1, 1, 1, then you have a penalty, so 11. 1, 1, 1, 1, 1, 1, 1, 1, then 21. 1, 1, 1, 1, and eventually it's $41. But the good thing that helps us out is that these intervals where it's cheap are getting longer and longer. Right here you have 10 cheap ones. Here you have 19 cheap ones, or 20 maybe. I'll just say 20. Here you have 40 cheap ones, and so on. So that means there's another way of amortizing the cost, as it's called. And that, so if you were a businessman, you would not want to deal with your customers like that. You wouldn't want to say, you know, most of the time it's just $1, but if you come at an unhappy time, it's $161. Instead, what you would do is you would just charge them $3 each time. And so what you then would do as the businessman is you would take the $3, and most of the time it only cost you $1, and then you put the $2 extra in a piggy bank. So let's see how that works. So after the first call, we now have $2 in the piggy bank. In the first 10 calls, let's see, we've accumulated $20 in the piggy bank for those 10 insertions that only cost us $10. Now comes call 11, and we have to pay the penalty for growing, but now I can take them out of the piggy bank. I've saved up for that. The customer gives me $3. I've saved up $20 in the piggy bank from the previous 10 customers, and that's more than enough to pay for the relocation. And when you follow it through, after the next 10 calls, I have another $20 in the piggy bank for now a total of $30. So the piggy bank has $30, and then call 21 costs me $20 for the relocation because there's 20 elements I need to move, but I have $30 in the piggy bank, so I have enough to cover it. And when you follow it through, it always works like that. Because there's longer and longer intervals where you collect the extra $2 and you save them all, and the cost of relocation grows at the same speed. So the cost of relocation, at some point you have to pay $1,600 to relocate that array, but you have saved, I think, $1,610 in the process, so you've saved just enough to cover it and to not run out of money. And so the thing is that each time the cost goes up by a factor of 2, but the interval during which you can set aside that extra money also grows by a factor of 2, and so they're exactly in lockstep. So that means that the average cost is $3. It doesn't matter how long the list is. If you have 1 million elements and you now keep this through for quite a bit longer, the average cost per insertion is still $3. It's a fixed number. It doesn't depend. It's the same for 1 million, for 10 million, for 1,000. So that's what's called amortized constant cost. So why amortized? It's a term from business. So to amortize an expense means that you don't write off the expense right when you incur it, but you write it off over 5 years or 20 years or something. Like if you build a factory, for example, you don't get to claim the expense right in the year that you incurred it, but you have to over 20 years or so. Each year you can say, okay, 1/20th or some such number is a part of your expense. And that makes sense for taxation. It makes sense because you probably paid through a loan and stuff. So that's how it works in business. And so here we're using the same rule. So where we're saying that we're pre-collecting some money so that we can pay for the expense of operations as they happen. And so the notation for this is O of 1 plus. So it means it really is O of 1 as long as we make a proper accounting of the cost, as long as we remember to charge enough in advance to pay for the occasional expense of operations. So it's not truly O of 1, truly O of 1. It means every step would have the same cost. So we have this O of 1 with these occasional spikes, but we can smooth out the spikes by charging a bit more. So if you can do that, then it's O of 1 plus. So this is, it's a bit technical, and I will not ever ask you a question in this class where I give you a completely unfamiliar scenario to reason whether it's O of 1 plus. So I hope you can understand the argument why this particular thing is, that you understand the trick of pre-charging for the occasional expense of operation. And so you just need to remember that you can do this in the case of an array list. Question? Yeah. Okay. Yes. Yes, thank you. Yes, for all practical purposes, it's exactly the same. So the plus is just there like as a footnote to say, yes, it is O of 1, but just not quite. Yeah. Yes?
So is this ever used in more complicated scenarios, like we have like n, log n, amortize?
I've never seen an n log n plus.
Okay.
No. I could conceivably think of an O of n plus, but Not in this course for sure. Yeah, I mean, I could think of an O of n plus, where, you know, most of the time it's O of n, but sometimes it could be more than that. So the O of 1 plus you see all the time, just so that, you know, one is aware that there is this occasional hiccup. So if we compare linked lists and array lists, and we'll look at doubly linked and singly linked lists separately. So to add at the end of a singly linked list. Now here, okay, let's do the easy cases first. So here's the case that we just gone through. To add at the end of an array list is O of 1 plus. That's because of that, you know, normally it just sticks it at the end, once in a while it has to grow. To add at the end of a doubly linked list, Professor Heller has shown you in gory detail the implementation of the doubly linked list, and one of its features was that that there's a reference to the first and a reference to the last node. And so therefore it is trivial to go to the end. So when you have a doubly linked list, now it's trivially easy when we have a new element here to hook this one over here and to reroute this one over here. Then of course there was a previous element here that you need to link up. But all of those operations are independent of how long the linked list is. Okay. Now it says here that to add at the end of a singly linked list is also O of 1, but that somewhat depends on the implementation. So if you look at the implementation that we had in the previous section, in section 16.1, that implementation was so whittled down to the most basic things, just so that there's not too much work in your understanding each of these operations, that it did not have a pointer to the last element. So now we need to imagine that it does have a pointer to the last element. And in fact, the cost of updating that pointer is really nothing. And in that case, it is possible to have this in O of 1. So the caveat here is it's O of 1 provided that the implementation is smart enough to really have a pointer to the last element. So now let's look at removing. So to remove from the end of an array list, it says here O of 1 plus, and that is because what actually happens if you look at the implementation in the Java standard library, when you remove elements, eventually it will shrink down the buffer. And that is so, you know, imagine you have an algorithm that grows the buffer to 1 million, and then it starts removing, and you don't necessarily want to keep the buffer at the size of 1 million. And we're not going to go through the math. You're going to probably do that in 146. It turns out that you have to be very careful about the cost accounting. If you resize the buffer and shrink it down by half, it's not O of 1 plus. You have to wait until the buffer is only 1/4 full. But if you shrink it, if it's 1/4 full, then it turns out that the accounts balance, and then it's O of 1 plus. So take it on faith right now and wait till 146 for the math. The math is not really difficult, but it's just enough math that we're not doing it right now. So these are both, you know, amortized constant time, and that's good. For a doubly linked list, removing at the end is trivial because you go to the end and then you reroute some of the links and you're done. For a singly linked list, it's O of n. So, and that seems unintuitive, particularly since I just said that you have a reference to the end. So, so let me try to draw this really quick. This is a linked list. Here's my last node. So I have a reference to the end. And now I want to kill this node. So why can't I just delete it? What's the hang-up?
You don't have a reference to the thing before the last.
Excellent. I do not have a reference to the predecessor. And so what I would have to do is I would have to know the predecessor. So right now the predecessor points here. And my unfortunate duty is I have to kill this thing and put a null in here. But I don't know where it is. Now, we could try to be clever about this. There's no law that says I have to have a reference to the last element. Maybe what I should do is I should always keep a reference to the one before the last. What's wrong with that idea? So, maybe instead of actually storing the last, I should store like the pre-last. Now removing is easy. I just say pre-last.next equals null. Oh, I don't even care about last. I'm not gonna have last. There's no law that says that I must have last. If I have pre-last, I can always find last. And anyway, it's just a private implementation thing. So in my private implementation, in Horstman's implementation of singly linked lists, I will always remember the predecessor of the last element. And now removing in an instant. Pre-last.next equals null. What's wrong with the idea? Exactly. Very good. Now, how would I find the new pre-last? Right after I've done that, I would now have to move pre-last to over here, and I can't do that because I don't know where it is. So that means that the only way in a singly linked list to actually remove the last element is there's no way of remembering its predecessor so that it survives more than one remove operation. The only way to reliably do it is to start at the beginning of the linked list, go a step at a time until you find that predecessor, and then that of course works. But that's an O of n algorithm. So no one has ever discovered a way of implementing a singly linked list where you have where you can do this in O of n time. Maybe you want to think about it, and maybe you will be the first one. All right, so I'll leave you with that, and more of all this on Wednesday.